Today we'll go for the concept of draft tubes. Today we'll go for the concept of draft tubes. Can you see the screen? Can you all see the screen?
Yes, sir.
Yes, sir.
Okay. Just I'll finish up the draft tube concept, and there are a few problems on the draft tube also. We'll do that. Means not only draft tube, it is connections. The draft tube is connected to the Francis turbine. Based on that, few problems are there. By probably today and next week, I'll wind up this module. Okay, and then I'll go for the last module. Draft tube. What do you mean by a draft tube? It is a conical. Anybody can define what do you mean by draft tube? Given that. Yeah, see here. Can you see the screen? It's a welded steel pipe or a concrete tunnel with gradually increasing in cross-section area at the outlet. Water after passing through the runner is discharged through a gradually expanding tube called as draft tube. The free end of the draft tube is submerged deep into the water. Thus, the entire water passage from the head race to tail race is completely closed. Hence, does not come in contact with atmospheric air. That means, see, this is the shape of the draft tubes, where the inlet of the draft tube is having a smaller diameter and exit will be having a bigger diameter. And it is a enlarged, means at the beginning it will be small in diameter and at the end it will be bigger in diameter. Okay, anyone, all the concept of all the draft tubes are same, but depending upon the application, they used to select which draft tube is required for which plant. See, these are all the functions. A reaction turbine is required to install above the tail race level for easy maintenance and work. Hence, some head is lost. The draft tube recovers this head by reducing the pressure head at the outlet below the atmospheric level. It increases the working head of the turbine by an amount equal to the height of runner outlet above the tail race. All these things we have discussed, and I've shown you video also, but still I'm going to. Next. Exit kinetic energy of the water is necessarily lost in the case of turbine. A draft tube recovers the part of exit kinetic energy. The turbine can be installed at the tail race level, above the tail race level, or below the tail race level. These are all the functions of the draft tube. So this tells about what do you mean by the draft tube, defining the draft tube, everything. These are all the classification of the draft tubes and their various percentages, percentage of efficiency. And here, functions of draft tubes. These three are important. Definitely they will ask, define draft tube. What are all the different types of draft tubes along with functions of the draft tube? They'll ask. While explaining the theory also, I told so many times, I told that it will be asked in exam. So along with that, this draft tube, there is some derivation in the draft tube. How the pressure energy is recovering, that has to be explained, right? So what I'll do, I'll draw a draft tube. Let us assume this is exit of the turbine. And we'll give this as section 1. I will draw the draft tube. You draw the draft tube. Conical edge, where the bottom portion should be dipped inside the water. So this is the water level. This is the level of the water. Portion of the draft tube is then I will take somewhere here at the bottom as section 2. Section 2 and 2. Okay. And this height, I will denote this as HS. And this height, I will take up as Y. And here, what is the pressure acting at this level? It will be left to atmospheric. So, P atmospheric. P atmospheric. And this water, whatever it is seeing here, this below the water level, this is called as tail race. Tail race is nothing but an exit water where from the channel it is from the exit of the turbine it goes to the channel. No, that is called as a tail race. So with this, we wanted to find what is the pressure head at the section 1. How to determine? Applying Bernoulli's equation at inlet and outlet of draft tubes. If I apply the Bernoulli's equation about inlet and outlet of the draft tubes, then what will happen? What is the equation? Along with head loss due to friction. Head loss due to friction in friction, just head loss due to friction. If I include that, then what will be happen? What will be happening by applying the Bernoulli's equation is P1 by rho g, inlet of the draft tube, plus V1 square by 2g. This is also inlet of the draft tube, Z1. This is the total energy at the inlet of the draft tube, section 1,1. That will be equal to P2 by rho g plus V2 square by 2g plus Z2. If there is no loss, this will be equal. As I told you, there will be some loss. If consider the losses, then you have to include that loss. Combination of these two losses will be equal. The head, if I combine the second right hand side, then I'll get equal to the value of left hand side. Clear? So this is what Bernoulli's equation applying between the section 1 and section 2. So instead of writing Z1, Z2 or Z1 and Z2 and P2, I will rewrite another way. See here from the figure, I'll write it. From figure, what is Z1? How can I write the Z1 value? From the reference, if by taking the section 2 as a reference, what is the Z value I can write? Z1 is the combination of HS plus Y. This is the height of Z1. And Z2, it will become 0. And what about this P2 by rho g? This will become P atmospheric by rho g plus of Y. So these are all I taken from the figure. All these three values apply to this equation. Then what will happen? We'll see. P1 by rho g plus V1 square by 2g plus of Z1 is HS plus Y. It will be equal to P atmospheric by rho g plus of Y plus V2 square by 2g plus 0 plus head loss. That is called HL. Correct? Simplifying, if you simplify that, then what all the terms will get cancelled off? This Y, this one will get cancelled off. Then something else will cancel off. No, this 0 is I can remove. Then left out is P1 by rho g. Because I want pressure head at section 1, that is equal to P atmospheric by rho g plus V2 square by 2g minus of V1 square by 2g minus of HS plus head loss. Correct? So in the proper form, rearranging in the proper form, I can write like this: P atmospheric by rho g plus of I'll take V1 before. because velocity 1 will be greater. So that I'll take V1 before. V1 by 2g minus of V2 square by 2g minus of head loss minus Hs. So he will ask you to determine or derive pressure head at the section 1 for the draft tube. This is pressure head at beginning of draft tube, or he can also ask you to determine the pressure at exit of the turbine. Pressure head at exit of the turbine. For both the things, you have to determine the same thing because the draft tube is connected to the exit of the turbine, right? So you can determine this. Copy this and let me know once it is done. So this derivation, he may ask you in the couple turbine chapter also, because there also draft tube will be there. That this derivation holds good there also. Wherever the draft tube comes into picture, they may ask you determine the pressure head at the exit of the turbine or determine the pressure head at the beginning of the draft tube. Both are correct because exit of the turbine and beginning of the draft tube is at the same point. We will do one or two problems in the draft tube also. Whether it's done?
1 minute, sir.
Okay, okay. Any doubts, you ask me.
Done, sir.
Okay. Now, one more small derivation, that is efficiency of the draft tube. This is not actually. We go for efficiency of the draft tube. Okay. It is defined as the ratio of actual conversion of kinetic head into pressure head at inlet of the draft. See, what is the function of a draft tube? It has to convert from pressure head to kinetic head. Kinetic head to the pressure head. That ratio, we are going to call it as the efficiency of the draft tube. So, efficiency of the draft tube is V1 square by 2G minus V2 square by 2G minus of head loss divided by V1 square by 2G. So, there is some bigger derivation. That derivation you won't ask. Just you should know what is the efficiency formula. So, because of that, directly I written the formula at the end. There, if I simplify the derivation, it will become means we have to convert the pressure head. Initially, we have to take the kinetic head, pressure head, everything, and then finally we'll reach to this stage. But nobody will ask you to derive that. It is not there. But just in the problem, they will give you to find out the efficiency of a draft tube. This is not B, this is a draft tube. They will ask you to determine what is the efficiency of the draft tube. So because of only that intention, I have given this formula, final formula. Okay, I have not derived here. Final formula I have given if they ask you to find out what is the efficiency of the draft tube. Here, so don't get this V1 and then earlier V1, don't get confused with that. This V1 is nothing but velocity of exit of turbine or entry of draft tube, and V2 will be exit velocity from draft tube. Say this is the formula for the efficiency, but as per my figure, as per the figure what we understood, this was a turbine and this was a velocity means penstock. Here whatever the velocity we are getting V1 and this is a draft tube exit. No, what is the velocity we are getting? V2 will be same as V3 which is going out. So this is, in that case V3 will be here and this case V4. So if these two are equal, if V3 and V4 are equal, then what will happen? Then I can write only three velocities. This is V1, this is called velocity 2 and this will be velocity 3. So can you write for considering this V1, V2 and V3? That means if the turbine is also given, considered, then how to write the equation? Then efficiency of the draft tube will be equal to V2 square minus V3 square minus of 2G HL divided by V2 square. Can you tell what is why I written like this? The above equation why I written like this? This is
V1 as inlet velocity.
this is considering V1 as velocity of water at inlet of turbine. Understanding? So while deriving the efficiency of a draft tube, what we assumed is just we removed this turbine and we assumed this as velocity 1 and velocity 2. This V3 as velocity, and we assumed this as V1 and V2 and derived. Corresponding to that, the above equation, this equation we got. But actually, if I include the turbine, then this will become V2 and this will become V3. So the above equation will be converted to this. V2 is nothing but exit velocity of the turbine or inlet velocity of the draft tube. V3 is exit velocity of the draft tube. Same thing above also it tells. But if we take only draft tube, then V1 and V2 will be. But here, including the turbine, we'll take V2 and V3. Anybody having doubts? You ask me. See, better you understand about this. Why V2 and V3 we taken instead of V1 and V2? Because in most of the cases, they won't ask you to just find out the efficiency of the draft tube. It will be asked with respect to the turbine only. Means turbine data will be given. At last, they will ask you to find out the velocity of the draft tube. Then in that case, if you use this equation, you will go wrong because V1 is corresponding to the turbine velocity inlet. That is not required. We want velocity of the draft tube inlet. So that you're supposed to take V2, V3. So you remember this formula rather than the first one. Okay. Just you remember this formula rather than first one. If you understood both the cases, then good, no problem. Is that clear? Oh. Once it is done, let me know so that one problem I'll solve today on draft tube. Very small one. You can easily understand. If you understood this, how we got efficiency and what is the notations, you can easily go for that problem. I have posted one question in the WhatsApp group. You all have to check out, or else I'll project it now. Okay. I'll project the question. You copy that question. This question is based on, yeah, copy this. Finished? Just within 5 minutes, I wind up this problem. It is very simple. Shall I go for the solution for this? Hello?
Yes. Yes, sir.
See, now he has given a draft tube. Now we are solving the problem on draft tube. Concentrate on draft tube. But before that, we'll write down the figure separately, so that we'll be not having any doubt to take the notations. This is turbine, and this is penstock. Then we'll go this here by V1, V2, and we'll take this as V3. So from the figure, you'll come to know now what is V1, V2, and V3. Exit of the draft tube is V3. Now we'll read the question. A conical draft tube having inlet and outlet diameters are, so diameter inlet of draft tube is equal to 1 meters. Diameter outlet of draft tube is 1.5 meters. Okay. So I have not taken capital D1 and D2. Just I written like this only. Okay, because no need to we should not get confused between the D1 of the rotor, D2 of the rotor. This is different and that is different. And the water with the discharge water at a velocity at the outlet with a velocity of 2.5 meter per second. That means at the exit of the draft tube, that is V3 is equal to 2.5 meters per second. The total length of the draft tube. Total length of the draft tube. You go back for the previous figure so that you can come to know what is the length of the draft tube I taken. So this is section 1 and section 2. Length of the draft tube I taken and not L. I taken HS plus Y. Because as per the derivation, we'll move HS plus Y. Length of draft tube is equal to HS plus Y. Combination of these two is called as how much? It will be equal to 6 meters. And 1.2 meter length of the draft tube is immersed in water. That means what is that? What is immersed in water? This length.
Right.
The length Y is equal to immersed in water. Y is equal to 1.2 meters. That means if I take this as a section 2 or this as a one bottom section, here the water will be immersed. Means the draft tube will be immersed in water. So this height is called as Y, and the remaining height from the center to here, it is called as HS. So the total length and the draft tube which is immersed in water. If the atmospheric pressure head, that is atmospheric pressure head, P atmospheric by rho G, this is pressure head, is equal to 10.3 meters of the water, and head loss due to the friction in the draft tube is equal to HF or HL head loss is equal to, he has given particularly head loss due to friction. So I written HL instead of HL, I'll write HF. Both are correct. Okay, no problem. Is equal to 0.2 times of velocity head at the outlet of the draft tube. That means V3 square by 2G. Velocity head is V by 2G. Correct? So exit he has given, so that I'll take V3 square by 2G. This is the velocity head. Find the pressure head at the inlet. He's asking P1 by rho G. Sorry. Shall I take this as, for your reference, I'll take this as section 2, and this as 3 and 3. So he's asking inlet of the draft tube. So P2 by rho G is how much? He's asking what is the P2 by rho G, section pressure at the inlet of the draft tube and efficiency of the draft tube. So directly we know the value of pressure head, right? What is the formula we are given in this figure? Finally, P1 by rho G plus P atmospheric is equal to P atmospheric by rho G minus of V1 square by 2G minus V2 square by 2G minus HL minus HS. This is if I consider section 1 and section 2 for the draft tube. But as per, sorry. See, as per the figure there, P1 by rho g minus of P atmospheric by rho g minus of V1 square by 2g minus V2 square by 2g minus HL minus of HS. This is by assuming section 1 and section 2 for the draft tube. But in the figure, in the present figure, we are taken 2 and 3. So that what will happen for the above figure? See, above a formula will become like this: P2 by rho g minus P2 by rho g, that is equal to P atmospheric by rho g minus of V2 square by 2g minus V3 square by 2g minus head loss minus of HS. The form, this is minus of HS. This is the formula. Above formula will convert to this way. What is the reason? Because while deriving, we have taken 1 and 2 sections, but while in the problem, we have taken 2 and 3 sections for the draft tubes. Wherever 1 is there, you substitute 2. Wherever 2 is there, I substituted 3. So get all the values. Check out whether all the values are known for us or not. If not, if unknown, we'll go to find out one by one. P atmospheric, see this, will mark with red color, so that will be, so this entire term I know, it is 10.3. V2 square by 2g, whether V2 square by 2g is given, V2 square by 2g, no, he has not given. We have to find out this, we'll find out. V3 square by 2g, yeah, V3 is given, divided by 2g I can do. Head loss, that is also given. HS, that is given. Only thing I should find out is, what is the value of V2? To find V2, let us use continuity equation. Q is equal to area of the draft tube 2, velocity of the draft tube 2, that is equal to area of the draft tube 3, velocity of the draft tube 3 at the section 3. Pi by 4 into diameter 2 square into, what is V2? V2 is unknown. That is equal to A3 pi by 4 into D3 square. What is D2 and D3? So here, if I check out diameter, I'll get D2. Here I check out diameter, I'll get D3. So that this will be D2, this will be D3 for me. D2 and D3 into velocity 3 is given 2.5. Everything is known here except V2. Take out V2 in this, meters per second. Substitute back here. If I substitute back, I will easily get. So just I'll explain the procedure, then I'll get P by rho g. I'll get P by rho g. I'll write this. I'll go for the next sheet and then I'll write it. If I substitute back, I will get P2 by rho g. How much meters? Then efficiency formula for the draft tube I given. What is the efficiency formula for the draft tube? Just now we are given, no? V2 square minus V3 square minus of 2g HL divided by V2 square. All the values are known here. So find out the efficiency of the draft. Here only thing is to find out this V2. How to find out this V2? Can you tell the answer fast? OGM sir, just a minute. OGM sir.